This is Neil Patwari. I'm going to talk in this video segment about what the shift in frequency shift keying depends on. And it turns out it's just really one thing. In memory FSK, we use the following basis functions as our orthogonal basis set. For FSK, these basis functions are all cosines multiplied by a pulse shape, but the cosines are at different frequencies. The first frequency is omega naught, and then we have omega naught plus 2 pi delta f, and then we have omega naught plus 4 pi delta f, and so on until the last one is shifted by 2 pi k minus 1 delta f. So this frequency in terms of hertz offset between neighboring orthogonal basis functions is delta f. The question is, this is just my notation here. We need to know what this delta f should be in order to keep these signals orthogonal. First, I'm going to figure out what delta f needs to be in order to make any pair of FSK basis functions orthogonal. And to do that, first, let's assume that our pulse shape is a rect function. That is, it's 1 over square root of t sub s between 0 and t sub s. We can solve this by looking at the inner product. When I multiply phi sub k, any two of these functions here, together I'm going to get the square root of 2 times square root of 2 becomes a 2. I'm going to have p of t be 1 over t sub s, because the two square roots of t sub s will become t sub s. My limits are going to become 0 to t sub s, and I'm going to have these cosine functions at the frequencies of those two signals, 2 pi times k times delta f times t. Once I multiply these two cosines together, I'm going to be able to use the cosine product formula to come up with what that product is, a cosine at the difference of the two cosine frequencies, and a cosine at the sum of the frequencies. When I use that formula, I have an extra 1/2 that comes out front. So these two values of 2 are going to cancel. What's going to happen is that this second term is very, very quickly varying. This 2 omega naught is going to be on the order of 10 to the 6th or 10 to the 9th. So when I do this integral, this term is going to have a 2 omega naught in the denominator, and that integral is essentially going to be 0. We've done this before, and so I won't belabor this point, but this term is not going to get anywhere inside of this integral. So what I'm going to be left with is the 1 over t sub s, and then the integral of this cosine, which is going to be the sine divided by the frequency from t equals 0 to t sub s. When I plug in t equals 0, this term is going to be 0, because the sine of 0 is 0. So really what I've got is the sine of 2 pi k minus l times delta f times t sub s on top, and the same argument in the bottom. Now k is not equal to l, right? So we're talking about two basis functions that are not the same basis function, because I know that when I use the same basis function, I'm going to get the energy, which should be 1 for an orthonormal basis. But for k not equal to l, that's the question I'm trying to answer. I'm trying to get this integral to be 0 for k not equal to l. So I know that in order for this fraction to be 0, what I need is the numerator to be 0. I need sine of 2 pi k minus l times delta f times t sub s should be equal to 0. And that means that this argument has to be a multiple of pi, m times pi, for some integer m. So that would be that m is equal to 2 times k minus l delta f t sub s. Well, k minus l is an integer, so I don't need to really keep that going and multiply an integer by an integer. I'm going to get an integer. What I need is 2 delta f t sub s to be equal to an integer. And that means that delta f has to be m divided by 2t sub s for some integer m. And what we call minimum shift keying, that has an m equal to 1. My delta f is 1 over 2t sub s, or 1/2 our symbol frequency. But it turns out that what we're going to do more often, we're going to use m equals 2. So that delta f is equal to 1 over t sub s, or the same as the symbol frequency. The symbol frequency is just defined as 1 over t sub s here. And this m equals 2, or delta f equals 1 over t sub s, allows my receiver to be easier to implement. And what we're going to talk about is a non-coherent receiver. To understand a non-coherent receiver, I first need to talk about a coherent receiver. And as you saw, what we do in a coherent receiver is, and here I'm going to make this explicit, we multiply by the cosine that is being received, and then we filter by p of t and sample at times n t sub s. In the coherent receiver, we need to have a phase lock loop that looks at this input signal and determines what is the phase of this incoming signal. So there's actually a phased locked loop that influences what cosine is generated here, because there's some time delay on the received signal. The transmitter and receiver don't have the same idea of time down to the nanosecond level. So there is some incoming cosine that has a phase difference between this cosine. And in order to get this signal exactly to match, we need to make sure that that cosine is locked to the same phase of the incoming signal. You can think of it as if we've got some extra phase here that the phase lock loop estimates and changes until the signal matches up with what is coming in on the input. But this is actually just one block of what's going on the receiver. This happens for every frequency. On the second row of the receiver, we're going to add a 2 pi delta f times t here. This is the frequency offset for the second frequency of FSK, and that's going to then give us the amount of the x2, this is x0, sorry, x1, and so on down the line until we get x sub capital K, and these then are going to then go in our decision block to decide what symbol was sent. So this is our coherent FSK receiver. The problem is that as the number of basis functions increases, this K increases, then the phase lock loop is operating only 1 out of K of the time. That is, that frequency omega 0 is only sent 1/k of the time. Frequency omega naught plus delta f times 2 pi is sent 1 over k of the time. So that phase lock loop then has less and less information in order to lock to the incoming phase. So this becomes more and more complicated and less effective as capital K goes up. And one way to avoid it then is the non-coherent receiver. So in the non-coherent receiver, instead of having a phase lock loop, we do something else. Instead, we have both a cosine and a sine. And what we get out of this signal when we multiply by both the cosine and the sine is we get the energy that is contained within the cosine and the energy that is contained within the sine. What we do is we then square these and add them together. And out of this sum comes the energy at frequency 0, the energy in the 0 basis function. It is contained as some amount of energy in the cosine and some amount of energy in the sine at that same frequency. This is just for the 0th basis function that is at omega naught. And we're going to then do that again for the next frequency. We'll copy all of this, except instead of omega naught, we'll use omega naught plus 2 pi delta f. And for the next row after that, we'll do omega naught plus 4 pi f, and so on until we get to the capital Kth basis function. This will go all the way down to the energy in the Kth, capital K minus 1 basis function. I'm sorry, I should have made this K minus 1 as well. But all of these energy values then are going to go in our decision block. Our decision block is going to be based on these energies. So the problem with the non-coherent receiver is what I mentioned earlier, that m equals 1 doesn't work for the non-coherent receiver. And that has to do with having both the sine and cosine be orthogonal at neighboring frequencies. So the outcome of this exercise is to tell you what is delta f, the shift. And what I'm telling you is that the shift delta f depends on whether we're willing to implement a coherent receiver or not. And that a more complicated receiver allows us to use m equals 1 and thus keep our receiver using less bandwidth. But a non-coherent receiver makes our receiver implementation less complicated, but it requires us to use more bandwidth. Now, I haven't even told you what the possible symbols are in FSK, and so I have to talk about that. FSK is really unique because it has the number of symbols equal to the number of basis functions. That is, there is exactly one symbol for each basis function. We didn't have this before. M was different than K in general. For QAM, we had K equals 2 all the time, and M could be very, very high. And here, we have exactly one symbol for each basis function, and the mth symbol is m is some constant, a, times the mth basis function. And S1 is equal to a times the 1 basis function. K equals m here. It doesn't matter whether I use capital M or capital K in these cases. If I draw the constellation diagram, they are particular. They'll seem very unique. So our symbols are on the axes a away from the origin. This is for the m or k equals 2 case. And for the m equals 3 case, which doesn't occur in practice, I can still draw the constellation diagram at least, and I'd have S0, S1, and S2 all being, again, a away from the origin and on one of the basis functions. So m equals 4, obviously I'm not going to be able to draw it, but if I were to draw 3 of the basis functions at any time, I'd be able to draw 3 of the symbols in that constellation diagram. And they're all going to be a away from the origin on one of the axes. One last thing, what is the average symbol energy? Well, it doesn't really matter what capital M is. All of the symbols are exactly a away from the origin, so the average energy is going to be a squared because every symbol is a squared in energy. You'll see in the Proakis and Salehi book, instead of using capital A for the constant that's multiplying the basis function, they use square root of E sub s, and you can see why that is.